Hi guys, it's Miss Montguire. The last thing we're going to talk about when it comes to the properties of water is its relationship to the terms acids and bases. Now, acids and bases are probably words you've heard before, but chances are you don't know much about them. You probably know a little bit like acids can be very corrosive. Your experience with bases are probably a little bit more limited, although bases can be just as harmful to organisms as acids. And you probably know that we measure how acidic something is using the pH scale, but beyond that, most people aren't all that familiar with what the term acid actually means. So before we can describe that, let's just review for a moment what water is like. So water, remember, looks a little bit like Mickey Mouse, and that's because the two hydrogens attach at an angle. Oops, that's about 100 and a little bit more than 100 degrees, and oxygen, the larger atom, is acts like it's negative, and hydrogens act like they're positive. Boy, Mickey looks a little angry. In any event, water, remember, is a polar molecule. We've got these charges, and that means that water is a very good solvent. Remember, solvent means basically that it can dissolve something. And the reason it dissolves something is because of these charges. Well, when water is near an ion or something, let's say sodium chloride, remember sodium chloride has a positive sodium and a negative chloride. The negative side is attracted to the positives on water, and the positive sodium is attracted to the negative on water, and so in reality it would be different water molecules that pull it apart. Well, sometimes water is such a good solvent that it actually gets pulled apart itself. Let me just clear some of this stuff off. So when water gets pulled apart, almost done. Alright, so when water gets pulled apart, what happens is we're left with one oxygen and one hydrogen hanging out with each other. And one of the hydrogen gets pulled off. And sometimes it can stick to other water molecules. So it's like Mickey Mouse has a large growth on its chin. And sometimes it hangs out all by itself. And when this happens, this thing is called hydronium. And so sometimes it's hydronium. Not sure if I spelled that right. I got a hunch I didn't. And then this thing is referred to as hydroxide. But this guy isn't all that stable, so a lot of times what happens instead is that the hydrogen ion will exist all by itself as just one hydrogen ion. Well, a hydrogen atom has one proton, one neutron, and one electron. So consequently, if the electron that this guy had, this negative electron that it had, is hanging out back with hydroxide, all this has then is a positive charge. So let's get rid of that. So all this has is a positive charge. So another way of writing this is a proton. There's just one positive charge. So this guy is called hydroxide. We abbreviate like this, OH negative, because it's still got the negative from this proton. And we can abbreviate this guy as H+. So that's like way more detail than you probably needed to know. But it's a little bit of background knowledge. So just to recap, here's kind of the shorter way of explaining things. water can dissolve substances, and when it does, sometimes what was H2O, Mickey Mouse, becomes a hydrogen ion, or what we call a proton, just the H. And sometimes, and not sometimes, when that happens, the other part becomes hydroxide, or OH. So, the other thing that a lot of people know about acidity is that we use the pH scale to measure it. Well, what the pH scale is it's just a concentration of hydrogen ions. So concentration really means how much of the solution is made up of hydrogen ions. Typically, not typically, sorry, always, the scale is from 0 to 14, where 0 basically means all hydrogen ions, and 14 basically means the entire solution is hydroxide ions. However, if those two are equal, then we say that it's a neutral solution. In other words, there's exactly the amount of concentration of hydroxide as there is hydrogen ions. So when we put these little brackets around things, that's kind of the chemistry way of just saying the concentration of something. So this, what it just means, and what you're putting your notes in this little equal sign, that just means the concentration of each of these two things is neutral. In water, that's a neutral thing. In fact, it actually is fairly rare that water will pull apart all by itself. It needs some kind of solute to help dissolve it. And so all by itself, there's very little hydrogen ions and hydroxide ions. It's just basically water molecules. So water is neutral, and they're equally likely to have each component. Most organisms, then, are also pretty neutral. They're very close to just having a little bit more hydroxide, or just a little bit more hydrogen ions. And so consequently, they're just very, very close to neutral. And I tried 3 times to try to make this graphic show up, and for some reason on this app it won't. But what this is basically saying is that this pH scale is a measurement of the concentration of hydrogen ions. And so if you're over near what would be 7 over here, it got cut off, there would be about equal amounts of hydrogen ions as there is hydroxide ions. But as you go, if blue is hydroxide, as you go lower on the scale, you tend to get more and more hydrogen ions than you do hydroxide. Got it? But an acid is simply a compound that has more hydrogen ions in the solution than hydroxide. So in other words, when it's dissolving something, it tends to make hydrogen ions. So we'd say that an acid is measured on the pH scale of anything less than 7. So the concentration, remember that's what the brackets mean, the concentration of hydrogen ions is greater than the concentration of hydroxide ions. So there's more of them. So some things that are acidic, obviously things that end in acid are battery acid, stomach acid. The acid in your stomach is actually really, really, really acidic. So much so that you have special mucus that lines your stomach, and if that mucus wears away, the acid will actually wear a hole in your stomach. If you've ever heard of ulcer, that's what's happening. But there's a lot of things that are actually fairly acidic that we don't always realize. Lemon juice, vinegar, soda, all of those, orange juice, all of those things are still fairly acidic. 2 is a pretty low acidity to talk about lemonade being that acidic. Even things that seem pretty neutral, you wouldn't associate at all with acidity, like bananas or like lake water, typically are. Even a healthy lake, we talk a lot about acid rain, but even naturally healthy, unaffected lakes have a basic acidity to them. And I just realized I said basic acidity. I meant a little bit of acidity, not basic like a base. Sorry. So just to make it clear again, remember this graphic got kind of messed up. If 7 is neutral, and that means that if hydroxide is in blue and hydrogen ions or protons are in pink, then as you go from having basically equal amounts of each at neutral, as you go to a pH that's less and less, there are fewer and fewer hydroxide ions, and more protons, until eventually at 0, it's essentially all protons. So this is a little counterintuitive. As the pH goes down, the acidity goes up. So bases are the opposite. If acids make protons, then bases make hydroxide ions. The hydroxide ions then would be in a larger concentration. Remember, this thing means concentration. So that means, in other words, in the solution, there's more hydroxide ions than there are hydrogen ions. And so technically 7 is not the pH. 7 would be neutral, but like 7.1, anything higher than 7, all the way up to 14 would be our basis. And if you look at the kinds of things that are examples, these should look familiar to you because they're all basically cleaning agents. So, oven cleaner, very, very strong cleaning agent, trying to get all that gunk baked down in the bottom of the oven. That's very basic. Soapy water, also very basic. Ammonia is used in a lot of cleaning, and that's a base. Even baking soda is used a lot of times for natural cleaning agents, and that is a base as well. You'll also notice that salt water is basic, and so Great Salt Lake, which is more salty than like a regular ocean, as well as just plain old regular oceans, are both bases as well. So sadly, this graphic wouldn't work either. And so just to remind you, 7 is neutral. 7 means, once again, that the hydrogen ions, which we'll put in red, are about equal to the hydroxide ions. I didn't count that out, but it looks about equal to me. And with bases, the further away you go from a 7 higher number, the less and less hydroxide ions you get. Until you get basically all hydroxide at pH of 14 and increasing concentrations on the way to 14. So for pH, once again, the lower the pH, the more acidic. So the way you could look at it is the higher the pH, the less acidic. Or in other words, the higher the pH, the more basic. Finally, the last thing we need to talk about is homeostasis, because in organisms, when we talk about chemistry, a lot of it comes down to homeostasis. Remember that homeostasis means that we want to keep conditions the same. That should be an E. And remember, we need to keep our conditions the same because a lot of our molecules in our bodies are proteins, and they break down very, very easily. Remember, we call that denaturing. If you remember the enzyme lab, most likely, hopefully, you found that the enzyme in liver, the catalase, didn't work very well at all of the different pHs that we measured. It only worked at certain pHs. That's because it breaks down otherwise. So we need a way to make sure that the acidity in our bodies don't change very much, because we're full of water. It's always dissolving things, and so it does have the potential to change. And so to prevent that, we have something called a buffer. So a buffer is a mixture that reacts with the acid or base to keep the pH within normal range. It's like, hey, you've got a really, really strong base, or really, really strong acid, let's say you've got an acidity of 2 somewhere in your body, well, then let's mix it, pH, let's mix it with something that has acidity of like 8 or 9. And consequently, they kind of balance each other out. This doesn't work mathematically this way, so it's not like we would average those out. But they balance something else to keep it much more neutral. So it's usually a weak acid or a weak base that our bodies use to balance out those really strong acids and bases. So if you've got a lot of acid, our body will use a weak base to balance it out. And a good example of that is antacid. So remember, your stomach has a lot of acid in it, and when that leaks up into your esophagus, that's the tube that leads between your mouth and your stomach. When that stomach acid leaks up into it, you feel heartburn. That's when you feel heartburn. That's just the acid kind of reacting with the tissue in your stomach, or excuse me, tissue in your esophagus, and it kind of hurts. If you've ever like vomited a little bit, you taste it. It's not a pleasant thing. And so if you're experiencing heartburn, a lot of times people will take antacids. Antacids are typically basic, and they help balance out the acidity that kind of leaks up into our esophagus. A good analogy is how we use the term buffer in everyday language. So sometimes we'll say that somebody or something is acting as a buffer. Well, one way to look as a buffer is something that prevents change. So if a buffer is preventing change in acidity, then it's preventing the pH from changing. But in everyday language, sometimes we'll say, oh, that person's acting as a buffer. What that means is it prevents the conditions of whatever you're talking about from changing. So a good analogy is, I've seen a couple of shows where somebody will say, hey, come with me to meet, let's say, my parents, and you can be a buffer so a fight doesn't break out. So in the TV show I'm thinking of, a girl was meeting her parents, and she wanted her boyfriend to come because she thought her parents would make a scene about something at dinner. And so by having basically a stranger at dinner, she thought the parents would be on better behavior. So the boyfriend was acting like a buffer preventing change in her parents' behavior. So if you've heard the term, that helps. If not, it probably just confused you more. So if you haven't heard it, just ignore the whole boyfriend analogy. But again, a buffer prevents change, and if we're talking acidity, a buffer is something that mixes with high and low acidity to prevent change or keep it right in the optimal range or the best range for the tissue. Okay, so that's it for water notes. The substitute's going to pass out some homework packets. You should be able to do most of the homework packet without looking in your book or anything like that, so I didn't arrange for the books to be with you today. You should have the first 3 pages done based on what you have in your notes, and then we'll do notes on the very last page of the packet when I get back, and you can then finish the packet up. Thanks for being on really good behavior for the sub. See you guys on Friday or Monday.